1 of the mini course, we will essentially do 2 examples and 1 definition. That's what it will take us a while though. Buildings are simplicial complexes, as we will learn at the very end of this part 1. And they're very regular, and they're typically attached to a matrix group, like a GLN or SLN. So we have to deal with a bit of linear algebra first, and indeed this is actually what my first example is going to be about. We'll talk about the final plane. So take your favorite finite field, Q, and look at a vector space, V, 3-dimensional over this field. So Q to the 3. And then from this we can construct a finite geometry, okay? So I give you the points and lines. Points in my geometry, it will be a projective geometry, so my points will be the 1-dimensional linear subspaces of V, and the lines, L, they're the 2-dimensional linear subspaces of the same vector space, okay? And then we can make the points be contained in lines by the obvious definition that comes to mind. We say a point is incident to a line L if and only if, like this, P is contained in L as a subvector space of V. Okay, so we have these subvector spaces, and they can be arranged like this. And then we can draw the incidence graph. So first, let's think a moment about the situation. How many points and lines do we have? If we have the finite field with Q elements, we end up having Q squared plus Q plus 1 points, and in fact, since everything is drawn to one another, that's also the same as the number of lines we see, right? For every point, the complement is a line, so they count up to the same number of things. And then each point, let's put this as an exercise. Exercise 1. First prove this, and then prove that each point is contained in Q plus 1 discrete lines. This is just counting how many vectors you can actually write down in a finite field, right? So the 1-dimensional things are spanned by a vector. If Q is really small, say Q is 2, then you can only have zeros and ones as entries anyway, so you end up with the same thing relatively quickly. So there's only 7 points and 7 lines in this case. And I'm going to draw the incidence graph in case Q is 2. Okay. So we end up with, as I said, 7 points and lines that can give 2 distinct colors. Which one is really better? This 1, 2, 3, 4, 5, 6, 7. Say these are the points, and then we have lines. Is this green visible? Yeah. No. They sit in between points. Some of them are already connected the way I drew it. And then there's more connections. So you can end up with circles of length 6 around this big graph here. I did not make a mistake. So yeah, if you draw the whole incidence graph, this is what you obtain. Some of you might know this thing, it's also known as the Hilbert graph. And we can label it with the points and lines in our 2 sets here. Let's do that. So a couple of points are really easy to write down. They correspond to the standard basis, 1, 0, 0, 0, 1, 0, and 0, 0, 1. I denote these by E1, E2, and E3. So E1 is, for example, this vector here over F2. And then the lines in which this thing is contained in, well, they're determined by the other two vectors, right? So it's contained in a two-dimensional subspace, for example, spanned by E1 and E2. So here you get the common span of these two, and hence both of them are contained. This is why I put an edge here, right? So they're adjacent if and only if we have containment. And then here we have E2, E3, and the third one I need to label this E3, E1, which connects back to E1 up here. Okay. So what you can see is from the standard basis, we get this little subgraph here, which I marked in so the standard basis, and in fact every basis gives rise to a little hexagon like this. It comes again with one-dimensional subspaces alternating with two-dimensional subspaces, and here we just put the vectors, oops, 3, and then their common spans, E2 and E3, E1 and E2, and E1 and E3. And it doesn't, there's nothing special in the standard basis, right? I could choose any basis containing 3 vectors. Whenever I do this, I get 3 one-dimensional subspaces spanned by the individual basis vectors, and 3 two-dimensional subspaces spanned by pairs. Okay, so this whole graph here, exercise, finished the labeling. This graph. It's not unique, but once you fix one more, then it will be unique. So you have to think a little bit how the adjacency works, and what the other 4 elements of the points are. And once you start labeling the rest of the graph, things will match. Okay, but for every choice of a basis, you end up with a hexagon in here, and in fact this whole graph is covered by these hexagons, and this is an instance of an apartment. And here we see already that for one, apartments correspond to bases, and on the other hand, the whole building will be a union of apartments. So this is already one of the main features in the theory of buildings, that they're covered by certain nice subcomplexes corresponding to bases, which cover the whole thing. So here there's 3 types of apartments. There's these hexagons with 5 edges on the outside and 1 cutting across. That's how I drew the graph. There's one where you follow 3 edges on the outside, 2 cut across, and then 1 additional one on the other side. And then there's a third kind. Can't be that I'm running out of colors. Let's use yellow, which is the most complicated one. Well, they're all the same in the end, but it's embedded in the most complicated way and looks like this. Okay. So, and then of course you can rotate the whole graph to get all the apartments in the entire building. Okay, that's not the end of the story. Let's observe a few more properties of this geometry we've just constructed, and let's start with the apartment. Okay. So I said that an apartment corresponds to a basis. For a basis, we can reorder its elements. Okay. So we can have elements of the symmetric group, which we can, on 3 letters, which we can realize as permutation matrices in the linear group acting on this vector space. And with these permutation matrices, we can permute the elements of the basis, right? I can renumber them and call E2, E1 and swap it. So this induces an action of the symmetric group, and we will call it W for reasons that will become clear later, on one of these apartments. And I can view it as generated by two reflections S, let's call it S1 and S2. Did I do it the right way? No, this should be S2. This should be S1. And here S1 corresponds to the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. And S2 corresponds to the matrix 1 in the upper left corner, and then in the lower 2 by 2 block it's 0, 1. This matrix swaps first and second basis vector, and this matrix swaps second and third. And with the two we can generate the whole symmetric group, which is the reflection group acting on this hexagon and reflecting on all the three hyperplanes I've drawn in this picture. This is an instance of a while group, or more generally, coset group. And that's another general fact we will see, that on an apartment in a building, we always have a coset group acting, and this coset group partitions the apartment into nice simplices, where in fact every simplex, in this case every edge, corresponds to uniquely to an element in our group. Okay, so here we can label the edges by group elements. So say we take this as our fundamental region, labeled by the identity, then I can carry this edge over here by applying S1, so I label this edge by S1. Same for, S2 on the other side. To get here, I need S2 followed by a reflection along S1, and then to get here, I need S1 followed by a reflection along S2. And down here, we can do either S1, S2, S1, or S2, S1, S2. So we end up with a relation for the product of the pair S1, S2, and it turns out that we can write this group W as generated by S1, S2. Both of these are reflections, they're elements of order 2, and their product has order 3. Okay, so this is a way to represent the symmetric group as a coset group. Again, more details follow later. Okay, so I want to highlight a bit more the connection between groups. So we take G to be GL3 over FQ, or SL3 over FQ, whichever you prefer. And this incidence graph. We don't know yet what a building is, but I'm telling you this is one. And in fact, it's an example of a spherical building, spherical since the apartments are spheres, in this case one sphere. Okay. So first, this group G acts on board and moves vertices of the same color. So it acts color preserving. It's transitive on maximal simplices, we call them chambers. In this case, it's just edges. And it's actually more than that, it's transitive on pairs of chambers contained in an apartment. And this is essentially, this is a base change phenomenon in linear algebra. Okay, so remember here, a maximal simplex, what is it? It's a pair of a one-dimensional and a two-dimensional linear subspace. So it's 2 vectors out of 3 in a basis. The basis is encoded by this apartment. Okay, so a choice of a maximal simplex inside an apartment is ordering a basis. So if I want to map this, say, this edge here, to some other edge over here, well, this of course I can do. I can map any one-dimensional subspace to any other one-dimensional subspace by some linear map and sending the 2-dimensional subspace along. What I have to check is that I can also send the 3rd basis vector along somewhere, and not just somewhere random, but somewhere I've chosen, right, to a chosen 3rd one. So this is essentially just saying that you can find a base change matrix between any 2 given ordered bases. Okay? So we have this very nice supertransitive, it's in fact called strongly transitive action of G on your space. And the stabilizers of our simplices, they play an important role. So we will investigate them a little more. So stabilizers. So we have, in this particular example, 3 kinds of simplices. We have red vertices, green vertices, and we have edges. Okay. So let's first have a look at the one-dimensional linear subspaces, namely the red vertices. So stabilizers of points. Since we have a transitive action, it's enough to look at the stabilizer of this vertex here, and then take left cosets of that. So we look at this point, E1. It's the which elements of G, say GL3, keep this point fixed. How do they look like? Anyone want to say it? Anyone say it?
They have a multiple of E1 in the first column.
There are multiple of E1 in the first column, so they look like this. And the rest?
Are linearly independent.
Yeah. For the rest, you're free, except that you have to guarantee that this is an element of G. Okay, so stabilizer of this thing in G is this particular subset, and we call it P1 thing. That's an instance of a special subgroup we will also encounter in the second talk this afternoon. So stabilizers in G of, so that was the red vertices, green, of the 2-dimensional things, and again that's enough to look at this one here. They look very similar. We can add now things in the span of E1 and E2, but we're not allowed to leave that, so we cannot mess with the 3rd vector we have. Same here. So we again end up with 2 zeros, but in the bottom row instead of the first column. Okay, for this P2. And then the stabilizer in G of our fundamental edge Z0, which is just the edge between the red and green vertex I've picked. This is just the intersection of P1 with P2, sorry, P2, which ends up being upper triangular matrices. And we call this B. So this group, P1 and P2, of G, of course. So this group B is really important. namely its cosets recover all the maximal simplices in our building, and also in a sense with that the whole building as a set of chambers, a set of maximal chambers. So observe chambers are in one-to-one correspondence with cosets of E, so with this quotient, and then we have lines in one-to-one correspondence with G mod, let's see, P2, and points with G mod P1, just the way we constructed things and due to the transitive action of our group. So we can also use these things to characterize when the two edges are adjacent in this graph. The edges G, G, and HB. So once we know one, the chambers are our edges. Yeah? In this case, just the edges. They're cosets of D, so I can write a pair of edges as G times B and H times B for G and H and G. G, H, G are adjacent, i.e. they share a vertex of color Pi, and by this I mean one of the either a two-dimensional vertex or a one-dimensional vertex, one of the green or one of the red ones, if and only if the element G inverse H is contained in Pi. So the left cosets have to coincide on the correct panel stabilizer, the codimension one, the stabilizer. Okay, I have to make space. I want to keep some pictures. Let's keep this right around it. So there's one last stabilizer I want to look at, namely apartment stabilizers. Okay, stabilizers. A node should be my favorite base apartment corresponding to the standard basis. Standard basis apartment. It's this one here. Okay. This is a node which sits inside my graph delta. It's the blue apartment in this picture over here. And I want to figure out which elements of my group G keep this apartment intact. So there's two ways to ask this, either pointwise or setwise, right? So setwise, I get a group which I like to call N, and this is just the monomial matrices over FQ. If I want to keep this thing just setwise intact, I can permute basis vectors, right? So I can look at monomial matrices and be fine. And then pointwise, it's also a non-trivial stabilizer. We end up with diagonal matrices, and this is called the torus. In our group. Okay, observe that N is the normalizer of the torus, and in fact we can recover this symmetric group on 3 letters from these two groups. So another exercise. N normalizes T, and N modulo T is isomorphic to sim3 in this case. Yeah? yeah, so here we can take this, in fact, to be a definition of our while group here. And this will always be the case for a building, that whenever we look at the quotient of the setwise versus the pointwise stabilizer of an apartment, we will always end up with a coset group. There's another property I want to mention. You can let's put it as continued exercise. You can recover the PIs from the Borel subgroup over there. I could have mentioned it already over there, as a union of two things, namely B itself with, in fact, this will end up in a disjoint union, a double coset B, SI, B, where the SIs are exactly these matrices here. So if, for example, look at S1, it swaps 1 and 2. So if it swaps these two, it definitely keeps their common span, right? So it fixes this green vertex here pointwise. So the stabilizer of this vertex here definitely has to do something with the element SI, and this is in fact what ends up being the thing. Okay, so these double cosets, they also play an important role in the theory of buildings, and you should think of it as follows. B corresponds to our fundamental alcove, our fundamental chamber C0 here. Multiplying with SI on the left is reflecting this in the base apartment to its SI neighbor along PI. And then messing again with B, well, it stabilizes your fundamental thing, but you've just moved this thing to a neighbor. So it messes definitely with this neighbor. Okay, and so this is some other thing in your building. In fact, it's a collection of other things in the building, because you're allowed to multiply on the left with all the elements in capital B. Okay, and the positions where you can end up if you act with something in PI is either you stay where you were, fix this, or you end up in this double coset. So this is an explanation of how you can think of this. We will revisit this disjoint union later, probably tomorrow when we learn about galleries. Okay, so far so good. One last thing I want to mention is the following property. We have what's called the Bruhat decomposition. So not only is this B good to recover the PIs together with the generating elements of our coxeter group, but the coxeter group and the B together are enough to recover all of G. And our whole group can be written as a disjoint union of elements in the coxeter group in this quotient n mod T, and then double cosets. And in essence, this is saying that from your base chamber, if you move to a different chamber in the base apartment with a little W in W, since this W is transitive on chambers in the base apartment, and then mess with something stabilizing the fundamental chamber, you're getting everywhere. Okay? In fact, this already tells you that topologically this is a wedge of spheres, all of which are based at your fundamental base chamber, because it's somehow this B on the left here flips around this, all the spheres containing your favorite edge, Z0. Okay, so this is carrying already a lot of geometric information, and we will talk about this in more detail this afternoon. So, just so that you've heard this before, we will cover this in the second lecture. This is an instance of what's called a Bn pair. And these Bn pairs, it's this B and this N, they're they're not only enough to get back the whole group G, but they're also enough to encode the geometry of this whole graph delta here. Okay, questions so far? Yes.
A monomial matrix, what is that exactly?
A monomial matrix. Yeah, very good. Thanks for the question. That is a matrix that has exactly one non-zero entry in every row and column. Yeah? So it could look, yeah, these. Yeah. Except that you're not forced to put ones. You can put whatever you want. But you don't have a choice in F2. There's only zeros and ones. But if Q is bigger, then you have a choice, right? So it could be more than that. So in fact, if we're in this particular example, then here it's just the identity matrix, right? There's not much room. But if Q is larger, then you will have room, and this quotient will actually be a proper quotient, okay? And W will consist of all the monomial matrices with all ones in the entries. Dividing out the torus means that you divide out all the scalar multiples of potential stars in the monomial matrices. Yeah, okay, so e.g. S1, S2. All right, further questions? Not the case. Okay, that's a building. That's not a Bruhat-Tits building. But the next one I'm going to show you is one. That's a Tits building sometimes. So the apartments in this particular example were copies of spheres. And in Bruhat-Tits buildings, apartments end up being copies of R to the n's for some n, and I'm going to show you an example with n equals 1, which is the smallest possible, and the only one that's feasible in a talk like this to cover. So 2, the tree for this 2. Okay. Okay, we go down one dimension. Because SL3 would already give us a two-dimensional huge object, which I'm going to show you tomorrow. It's too big for today. Okay, so here, in order to actually achieve this, to be able to construct, again, this is going to be a graph. For SL2K, we want SL2K to act on it again, but we want this graph not consist of spheres, but consist of copies of the real line. Okay? In order to achieve this, we must have a more complicated algebraic situation. So we want K to be a field with a valuation. So for example, in this case, let's look at the p-adic completion of Q together with the valuation U that takes us to the additive group of the integers. Okay, so a valuation is for one map that satisfies the following. Yes, I did use X. It's X. If you evaluate on the sum of two things, then this should be larger than the infimum of u of x, u of y. And what we can, for example, do is if we take it's QP, so I should use UP, the p-adic valuation of a quotient A divided by B will be n, where n is such that A divided by B can be written as the nth power of P times some A prime divided by B prime, and A prime and B prime will not be divisible by P. Okay? So I look how many P's are in A divided by B, sorry.
Shouldn't this be the reverse inequality?
should this be the reverse inequality?
Because it should be some kind of triangle inequality.
It should.
I think that's for the norm, reduced by the valuation. Then you get
The reverse, yeah.
Oh, yeah.
The revaluation
Yeah.
should be like this.
Yeah,
Yeah,
okay.
the triangle
Yeah.
inequality is.
Polymetric, which is the
If you take the
Yeah,
shorter
yeah,
of
yeah,
two
of course.
sides, that's
Sorry, yeah.
at most as long as
You're
the
right.
third, yeah?
Sorry.
Okay, so that's the correct.
Yeah.
Exactly, because it has to be something
Yeah.
like a triangle inequality. Okay. Okay, so this is what we, for example, can take, and then we take the completion of Q with respect to this thing. Okay, so the precise details are we need one other convention. We want 0 to be mapped to infinity to not mess with this increment condition. From this we get a bunch of associated things, namely first a valuation ring, call it O, or script O. It's all the ones where the valuation is greater or equal to 0. So in our example, let's maybe do this with color. So if we have QP and this valuation, then here we end up with ZP.
Petra?
Yes,
I think you need to say something about the product of xy,
I need to say something about
about the valuation of the product.
It's the product of the valuations. Yes.
Some.
Sorry, the sum of the valuations. Yes. Yeah, should I write it? Yeah, thanks. Yeah, I'm not going to go into details about valuation theory. That would be yet another mini course, okay? Which you, if you want to classify buildings in the end, have to understand and do. But that's not what we're going to do today, okay? So we really look at just, yeah, but thanks, that was missing. Okay, so we end up with the valuation ring, which is ZP. We need what's called a uniformizer, call it pi. This is just a thing, an element such that the its value is 1. So here we could simply use P. Yeah, so if you P is P divided by 1. So its value is 1. And then the third and last, we need the residue field, which I want to write as K. And this is simply all divided by the uniformizer times O. And in our case, this ends up being the finite field of P. Okay? So, yeah, this should look familiar. Within SL3 over FP in the first example, and this is not a coincidence, as we learned it. Okay, again, we're going to do some linear algebra. We look at V now to be K squared, a 2-dimensional vector space over, say, QP in our example. And we look at lattices inside. And by lattice, I mean, let's call it L, finitely generated O modules. And okay, so think of this as picking a basis and then multiplying the basis only with elements in O. Okay, so for today, this is enough. So whenever we have two basis vectors, such a lattice is produced by taking linear combinations over O. Okay. Now, if we multiply with something in K, this might one of the basis vectors with something in K, especially with the uniformizer P, then this would produce another different lattice, right? Because something that's not in O will definitely mess with this whole sublattice. Okay, we're not only interested in lattices, but in equivalence classes.
Are you missing that? So R also has to generate V as a vector.
Yes, thanks. Generating V. We want only the ones of top dimension. But this is generating over K. I really want them to be top dimensional. Yeah. Otherwise, so here it's going to be a pair of linear independent vectors defining a lattice. But I want to take. I want to only allow lattices up to homotety. Namely, if I rescale both vectors at the same time with the same element in K, I don't want the things to consider different. Okay, so this is my objects, the classes of these lattices. So if I have these classes, them to be my vertex set of a graph I want to define. Okay, so, and now I have to declare the edges. So L is adjacent to some other class L prime if the following holds: if there exist representatives and L prime of these two classes such that L prime is contained in L, which is contained in the pi multiple of L prime, or the thing on the right hand side is saying if you divide L by L prime, or L prime is in L, and divided by L prime, you end up having K. Okay. So this is. Did I flip it?
The containment.
Which
The
containment?
pi.
Send the inside.
So L
Yeah,
prime.
This one?
This one.
L is in here.
No, pi and prime.
Oh, here was a prime missing, you're saying?
No, the pi should be on the left.
Here?
Far left.
Here? Okay, sorry. No, but then it's wrong, because then this will not be the same as this.
We change the price.
Yeah, something prime.
Yeah, you changed. Someone changed. So, okay, I write what I had. L. So, let's put it like this, and it definitely matches this one. Yes, I don't know what I had before. Sorry. So I always get confused. Okay, so this is what we want. In other words, this is saying you get one. So one is definitely contained in the other, and then you get the reverse containment by dilating the smaller one by the uniformizing pi. Okay, so that's what we want geometrically, what you should imagine as lattices in the K. Okay, so theorem. This graph will so obtain graph with a tree without loops, i.e. all vertices have valency greater or equal. In fact, more about here we have every vertex has valency q plus 1, and the tree, let's call it TQ. TQ is covered by 5 infinite lines. There will be apartments, and again they correspond to order spaces. The two bases. Sorry? Q is P, sorry. Where is another Q here? P. Is there another Q somewhere? Q is
No.
T, P is corresponding to the bases. Okay. want to draw this, at least a piece of it. Okay, so by construction, SL2 acts on this thing, right? Namely, if I have a matrix in here, then I multiply it with a basis giving me a lattice. It will definitely be a different basis providing a different lattice. What one has to check is that adjacency is preserved. So that should also be clear since we're dealing with SL2 here. So in the last example, you had a choice whether you want to take GLN or SLN. Here you don't. You have to take SLN. Okay, let's draw it. At least a piece of it. So given the standard basis again, E1, E2. I claim that this gives us an apartment, okay? So a lattice, so one lattice class is given by this. We take the O-span of E1 and E2 and take its homothetic class, okay? So this definitely is a vertex in our tree. Then what I claim is the following. You can multiply one of the two things, say E2 with a uniformizer, and take this thing, and you get a different vertex. Namely, well, they can't be the same because one is multiplied by something with valuation 1 and the other isn't, okay? If we take multiples with, if we take classes with respect to O, then we will never get one out of the other. It's not so hard to check this containment condition. So there's an edge here. And then it actually continues like this by taking powers of the uniformizer. So I guess you get it. So here you will have pi to the 3 2. And to the left you take negative powers or p on the other side. So this will be E1. Pi to the minus 1, E2, or same class is produced by pi E1, E2. So I like to put it with the minus 1 because then you immediately see that this is isomorphic to the integers. Because the only thing that decides where you are is the power of the uniformizer you've plugged into the set. Okay, now there's branching. There's one branch at every vertex. We have here what was it, Q? No, P. P plus 1 regular tree. And let's do one thing here. This is E1 and then E1 plus E2. And the class of this here. Again, every other basis you choose will give you another line produced in the same way we did here. You plug in the uniformizer in the second spot, and then you have to figure out which ones are actually producing the same homothetic classes in order to get the whole tree. Okay, so what do I want to say? Stabilizers again. Stabilizers. Okay, we agree that SL2 acts, and then let's just look at stabilizer of my favorite apartment, which corresponds is apartment corresponding to the basis containing E1 and E2. Yeah? The stabilizer of this base apartment, again we look at it setwise and pointwise. Setwise, it's again n with entries in the entire K, right? So I can multiply with things in my defining field K. I end up in a different, potentially different lattice class, but it will never kick me out of this base apartment produced by my standard basis vectors E1 and 2. And point-wise, stabilizer looks a little bit different. I can multiply with diagonal matrices, but this
Sorry,
does.
what's N of K?
Sorry?
What is N of K?
N of K is the same N as it before, so it's monomial matrices.
Okay.
Yeah, but thanks for asking. With entries, I wanted to save time in the wrong spot. With entries in K. And I take diagonal matrices, but only with entries in here, because I want to fix it pointwise, so I'm not allowed to leave the O span I have in my vertex, right? So vertices are sensitive to multiplication with K. You get kicked out of your vertex. But you can mess with things in O. This is not seen since we take multiple classes. Okay, so we have this. And what we get is, again, here N of K divided by T of O is a coset group. Let's call this W. And in this case, it's the coset group, which is a semi-direct product of a reflection at the origin, say at my favorite lattice E1, E2 lattice class, given my E1, E2, and then translations that preserve color. So for reasons I cannot explain right now, vertices alternate in color, and we have a copy of Z1, Z2, semi-direct product T, and this T here is in fact the same T as this T up here, and this acts color preserving. Color preserving. Translations. Yeah, and I'm afraid there's no time for the definition. You have to wait for this afternoon, and I'm going to stop here at the end of the second exam. Thanks.
Beautiful lecture. Do we have questions?
Do you know who first constructed the tree for SL2?
I learned it from Sel's book
Right.
on trees, but
Maybe
I'm
it's
not.
the one that came up with it.
I'm not sure whether it was Sarah who came up with it.
No, it was done.
Eva Hohl.
Anyway, sorry.
Yeah, sorry, that is a dark spot in my knowledge of history of this topic. Sorry.
Could you please state again with more writing why the Bruhat decomposition implies this homotopy equivalence with the wedge of spheres? I didn't quite catch it.
Yeah, the homotopy equivalence with the wedge of spheres. Okay, so remember we have this complicated graph here, and you have your favorite edge here, B0. B is the stabilizer in the roughly the symmetry group of this thing, of this edge. So what does it do? It permutes other edges. It acts nicely and maps basis to basis, since we're in a linear algebra setting, right? Our group G is a linear group. It was GL3 over affine field. And a basis corresponds to one of these hexagons in here. Take a little b in B, it maps your basis, i.e. your hexagon, to some other hexagon containing the same edge, because it has to fix the edge. Okay, so it not only permutes anything inside the graph, it permutes all the hexagons containing this edge. And then from the Bruhat decomposition, you know that this permutation must cover the whole thing, since we know that it equals all of G, and G acts transitively on the whole graph. So wherever you want to go, say here, you can go there by going someplace else in your base apartment, which is W0, and then apply something in B. So this would be BW0. And this gives you that, in fact, you see the whole graph by only looking at hexagons containing one edge. Fix a favorite edge and only look at hexagons containing this edge, then you cover the whole graph. This is an easy exercise you can do with a drawing. And that is enough to see that you have a wedge of spheres. Yeah?
I guess I understood the argument.
Here's your base point, and you have your spheres somehow glued to that base chamber here. That's a consequence of this difference. Well, modulo, all the details are not filled in, right? Including the proof of the Bruhat decomposition. But roughly this gives this.
Just a question about when you write bases, you mean ordered bases?
I do not mean ordered basis. Do I mean, here I mean ordered basis. Do I mean ordered basis? I don't need to order it.
They span the same letters.
Yeah, they span the same letters, no matter which order you take them. Yeah, you just take a basis, no ordering needed. For the bijection to the integers, you need the ordering the way I organized it, because you always want to put it on the second factor, so you have to keep the second factor the same throughout your construction, but otherwise you don't need an ordering here. Same here, no ordering needed. Okay.
I was a little confused about what happens with the pointwise stabilizer, because
Yes.
pi is an O, right? So
Pi is not an O. Wait, pi is an O. Yes, sorry. That was,
sorry? Yes, if you take one like one pi.
but you have to,
I don't usually one.
Yes.
That's a point. Yeah.
yes, determinant is one.
Yeah, okay, thanks.
But if you take pi inverse and then pi, and then apply the homotopy with pi.
Say that again, I could not hear what you were saying.
Take the lattice generated by 1 and 3.
This one,
Yes.
yes,
Then you multiply it with pi inverse pi,
yes,
and then you get the lattice pi inverse e1, pi e2. You can. This is in the homothetic class of pi. No, of e1, pi squared e2.
I couldn't follow.
This is kind of different.
Maybe we can do this afterwards in a little calculation on the board if you want. It's hard to not
Pi
write it down.
inverse.
No.
No, it's for sure. This is the point. I mean, do a little calculation on a piece of paper after lunch, and you will see that it's not hard to see. Yeah.
More questions? If not, then we thank Petra again. Just a little announcement about exercises. So we have